Welcome back to Projects with Everyday Dave. The world is an unstable place, and just a little bit of knowledge can make the difference between life or death in an emergency. Are you prepared for a hurricane or a power outage in your area? Today, I'm going to show you everything you need to know to make a simple 12-volt off-grid power setup for emergencies, camping, a cabin, or your van or RV. I'm going to review the tools, the materials that you need to set up a solar-powered system and a very simple emergency-only setup. I'll show you the performance you can expect to get from this setup and compare it to some off-the-shelf solutions like this Bluetti EB70S. This video is not sponsored, so even though some of these materials were donated by the manufacturers for this project, you can help pay for the rest by hitting the like button and using the affiliate links in the description if you end up purchasing some of these materials for your project. Not to mention the fact several of the manufacturers have offered discount codes for my viewers, which you can also find in the description below. All right, let's do a quick overview of the tools. So first, you'll probably want to get a heat gun to shrink the shrink tube. You'll probably want some wire strippers. Now, these are really easy and nice to use, especially if you're new to wiring. These make it really easy. You'll need some kind of adjustable wrench or a set of wrenches to tighten things up. You'll need a set of wire cutters. This is a very nice tool for cutting the sheathing off of very heavy gauge wires, but you can also get away with a utility knife. You'll need some kind of a crimping tool for crimping the lugs on your wire connections. There is a cheaper version than this one. It's a hammer style, and I'll put a link to that in the description below, but this one works really well. There's a much more expensive version of this that is essentially exactly the same. So this is the one that I recommend. I paid for it myself. It works great. Another thing you'll probably want to have is an MC4 crimping set. This one from BougeRV is really nice because it comes with the crimping tool, it comes with multiple MC4 connectors, and the tool that you need to tighten those up and easily remove them when you want to disconnect your system. So this is a really inexpensive, simple kit to get. Now, it's also going to be really helpful if you have some kind of a meter. Now, I've got two represented here. These are a pretty good value. They're inexpensive for what they provide. This one is really easy to see. You can stick it in your pocket. It auto finds voltage, things like that, so you don't have to know anything about it to use it. This one is a little bit more advanced. It has a clamp meter, which allows you to measure current, which if you're doing high current things, it's really nice to be able to do that. And this particular one can do inrush. Now, you don't need inrush for this project, but if you're wanting to do an off-grid setup and you want to see if your AC unit or something like that has a tremendous amount of current at startup, that's the inrush, this meter will measure it. There's a less expensive version that just does current and not inrush, and I'll link to both below. So that's the main tools that you're going to need. So now let's look at the materials. If you're going to do the solar-powered version, you'll need solar panels. You can use these hard-backed version to put on your roof or mount them outside on a rack. Or if you want, you can do a portable version like this Bluetti foldable one. The foldable versions are a lot more expensive. So if you're on a budget, you'll probably want to get some fixed panels. Next, from a wiring standpoint, you'll need some 10-gauge PV wire. PV wire is UV stable, so it can be outside. Now, if you're on a budget, you can get cables already made up, like these ones from BougeRV. They have MC4 connectors already on them, so you won't need this kit to put those on. But if you're going to do a lot, you might want to get some wire and the kit, and you can make them all yourself. You may also want some Y connectors. These will allow you to connect multiple panels in parallel. You'll also want a way to manage the wires. You can use some of these stainless steel clips, or you can use zip ties. If you use zip ties, you want to be sure and get UV stable ones like the ones I'll link below. Then you will need a solar charge controller. The one we're going to use is this BougeRV 40 amp solar charge controller. And what I like about it is it can take up to 150 volts in. So you can start with a small system and you'll have space to expand it later. And it has a temperature monitor for your battery. If you are going to mount your panels permanently, you'll need some mounting hardware. And if they're going to be on a roof or something like that, you'll need one of these glands that allow you to bring your solar panel cables in and put a hole in the roof and have it protected and sealed. For the power storage side, you'll need a battery. Now, this is a lithium iron phosphate battery, and this is a really great solution, but I have a couple of other options that I'll show you as well. These are two Enjoy-bought lithium iron phosphate batteries, and I'm going to put them together in parallel so we'll be able to double the capacity that's available. And then this is an AGM battery, which will represent our standard automotive style battery, and you'll be able to see the capacity and setup for that as well. To get our power from our storage location to our components, you'll need an inverter. And this is a 1500 watt alpha inverter, and that's a pretty good size for powering most things that you'll need at the house other than like a large air conditioner, but you can use a microwave and pretty much all your other components. Then you'll need some lugs for securing your wires to all your components, some heat shrink tube for sealing all of those connections. Then you'll need a fuse or a breaker. Now the fuse is a little bit cheaper, but the nice thing about these breakers are you can easily turn them on and off to connect and disconnect your system without having to connect and disconnect wires. And for the extra 10 bucks, I think it's worth it. And then finally, to connect your inverter to your battery and your charge controller to your battery, you're going to need some special wire. Now, the inverter is 1500 watts, and at 12 volts, that requires a very heavy-duty cable. So we have a 1/0 cable here, and you can get a kit. It comes with the lugs. And then I have 6-gauge regular wire you can get at any home store, and that's what we'll need to carry our charge controller power to the battery. And then finally, if you're not going to use solar as your power for charging things, you will need an AC charger to charge your battery up for the very simple emergency system that we'll look at. Now that we've gone over all the components, let's start putting it together. Okay, I just grabbed a scrap piece of plywood big enough to lay out the components. I put the inverter on one side so I can have my AC coming out and make sure there's plenty of room for the power wires to come in, and the solar charge controller on the left so I can have the solar panels come in the bottom and the power coming out to the inverter for that. And then I roughly place my circuit breakers, and in this case I will trip each one of them so that when I'm connecting things up, I know that power won't be running through it. There's an order in which you have to power things up, and we want to make sure that we don't accidentally put power to something in the wrong order. And then these have a battery or line in and an auxiliary or load out, so each one has to be oriented correctly. The battery or source will be where the PV lines will come in, and the inverter will be the load for the PV side. And then this breaker, the charge controller, is the battery or source, and the inverter will be the load. For this breaker, the battery will be the source and the inverter will be the load. So now that we have them roughly placed out, we can start putting our wiring in. If you're going the low-cost route, you could just take this extension cable, remove the insulation from the ends, and connect it to the PV input terminals on the charge controller. But you want to make sure that the panels themselves are not connected until you have battery power to the unit first. In my case, I want to use a breaker in between the PV source and my controller so I can turn them on and off easily without having to disconnect the MC4 connectors. So I'm going to make some wires that run from this to the breaker and have some MC4 connectors off the end, and we'll just use this as an extension cable by adding MC4 connectors to the other end. So let's wire it up. With everything mounted, it's easy to size every wire for where it goes. I've relieved the lugs, removed some insulation, and I can measure out exactly how much I'm going to need minus the lug. So we'll want to cut it off here and strip it to there, and that'll give us a nice length of wire. A nice solid connection. Put a little heat shrink tube on it. Now we just need to make our MC4 connectors. For the positive end, the male connector will be the positive wire coming from the solar panel. So we'll need to put a female connector on the positive wire on the receiving end, and then the negative will be the male connector on the receiving end. So let's make those. The female connector uses the male pin, so that can be confusing. And then pro tip, just set the pin in the tool first, and then slide your wire in, crimp it down. Make sure the gasket faces up. The pin should snap in snugly. Then this tool helps you tighten it up. Then put our lug on the other end. Now we have our MC4 connector set up, so we can bring our solar panel power directly in and easily just connect it to these MC4s. Circuit breaker's off, and if we want to connect them, we can just turn it on when we're ready. All right, now let's connect the controller to the inverter. For the PV input, I used a 30 amp breaker and 10 gauge wire. For the charger output, we'll use 6 gauge wire and a 50 amp breaker. So let's wire that up. Now I'll set this to 6 gauge. It's a very nice, robust connection. I'm going to have this loop with the red wire. It's going to hang off the bottom a little bit there. Now that the charge controller and the inverter are wired up, it's time to connect the battery, which requires a much larger wire. We're going to use 1/0 for this so that we can have a little bit of length and not be worried about high temperatures and line losses. You can get this as a kit. It comes with the black and the red, as well as the required lugs and the heat shrink tube. Now you want to get this special battery cable. It has very fine wire in it, so even though it's super thick, it's still very flexible. In this configuration, I want to be able to have the breaker on the top of the battery, and then I'll have a negative and positive takeoff from the end of the battery. So I just need a piece of cable to go from the positive terminal to the back side of the breaker, and I'll put a little bit of an arc in it to give me some flexibility. So that's what size I need. Wow, that's really tough. Wow. I can strip the ends. There we go. Now when I do this end, I need to make sure it's indexed. The cables are very hard to twist once you put them together. So if I have it laying flat, I can put an index mark. So when I crimp it, I'll make sure it's oriented properly. There we go, indexed. There you go, nice heavy gauge cable, secure and ready to go. If you weren't going to add a breaker, you could simply take the extension cable from BougeRV, which has MC4 connectors on one end and bare wire at the other, and connect it directly to the solar charge controller. But because we added a breaker with some MC4 connectors, I'll just take the included connectors that come with the cable, add them to the end, and we'll turn it into an extension cable. When you're making an extension cable, you will always have a male on one end and a female on the other. So in this case, our red wire already has a female connector, so we'll put the male connector on the end of that cable, and the negative wire has a male connector, so we'll put the female connector on the other end of that cable. There we go. Now we've turned it into an extension cable. We can connect our solar panels to our charge controller and have power available. Now with the breakers in the open position, I can combine the 1-aught battery cables that I've made up with the 6-gauge cables from the charge controller on the posts of the inverter, and the other end directly connect to the posts of the battery and the battery breaker. When starting up your system, it's important to do things in the right order so that you don't damage the equipment. One of the connections that's critical is the battery to the inverter. Now, you can get one of these resistors, they're really inexpensive, and use it to pre-charge the capacitor without the instantaneous jolt you would get by just contacting this large gauge wire to the battery. In order to pre-charge the capacitor, we'll turn on the breaker so the battery hot side is connected, and then I can just connect the terminal through the resistor to the battery and just hold it there for 10 seconds. Depending on the size of resistor. That will pre-charge the capacitors so you won't get any arcing when you connect the battery, and it helps protect the equipment. Now see no spark. Now that the battery is connected to the inverter, we would be able to turn on and operate the inverter. The second step is to connect power to the charge controller. You cannot connect the PV power before you connect the battery power, or you will damage the charge controller. That's one of the reasons I have the breakers, so I can control that independently very easily. So now that we have power to these cables, I can flip this breaker. Now you can see the charge controller starting up, and it shows the voltage of the battery. It's 12.8 volts. Now I can flip on the breaker for the solar panels, and now you see the light lit up and it's charging, and that's why the voltage is starting to push up a little bit. 13.1 volts, so we're running power in. Now we have PV power and battery power available to our inverter. I can turn the inverter on and do some testing. I have 108 volts on the AC side and 13.2 volts available on the DC side. Let's try some loads. Start with a big load. 4 amps. 8 amps. No problem. Pulling the voltage down on the battery. Nice. Well, looks like it works. Let's run some tests. All right, I brought my son Jordan down here with his oscilloscope so we can check the sine wave on this inverter, which claims to be a pure sine wave inverter. So Jordan, show us how it's done.
Okay, so we've got this oscilloscope here, and it's hooked up via this probe in not the safest configuration, but it should work. We can see on the screen here that we have a really good sinusoidal waveform coming out of the inverter. So I also have a heat gun hooked up to it. It's going to draw a lot of current from it, and a lot of these inverters will break down their curve when you draw a lot out of them. So let's put it under load and see what happens. So with the heat gun running, you can see there's a little bit of distortion around the top and the bottom of the curve, but overall it keeps a really good sine wave shape.
So definitely is a pure sine wave inverter.
Yep, it is a pure sine wave inverter. So now if we look at the inverter itself, we can see that we're drawing about 9 amps at 110 volts with a 12.4 volt input. So because power in has to equal power out, and power is current times voltage, we're going to be drawing a ton of current on the input side, about 10 times more than the output. So I actually have a clamp current meter here. So if I just come around to the battery side and clip this around, so we're drawing about 91.4, 91 amps, which is a lot of current. So this is one reason why you might want a higher voltage battery, because it'll draw less current to get the same amount of power out of it. And because wires are rated for the current, you can get smaller wires and save some money there. So from that we can see that you might want to pick a higher voltage battery in order to draw less current from your batteries. Because the wires are rated by the current, you can use a smaller gauge wire and save some money with a higher voltage system.
Sometimes people pick a 12-volt system because they want 12 volts because they have 12-volt devices, but if you're not tied to that, it's definitely better to have a higher voltage battery.
Absolutely.
All right, Jordan, thanks for using your oscilloscope and checking out the inverter. And now we can do some full-scale testing.
No problem. Sounds good.
Thanks. Okay, we finally have some sun out. The unit is running. We have 6 amps coming in from the solar panels, 33 amps coming out from the solar controller, which means we only need 2 or 3 amps from the batteries. So the solar controller is almost directly running the dehumidifier from solar panel energy. 35 amps. Controller's almost maxed out with those 6 panels I have out in the yard. They don't even have full sun yet. Stick a temperature probe up in here. And we're at 140 degrees Fahrenheit, 60 degrees Celsius. Things are getting pretty toasty. 5 amps coming in, probably around 90 volts. And 33 amps going out. It's just about maxed out. Only a couple amps coming out of the battery. Solar panels are almost 100% powering the dehumidifier. 150 degrees. Woo. It's very warm. A little fan on there brings it right down. Just a quick overview of the solar charge controller. The BougeRV 40 amp charge controller has worked great. Now the first one I got from them had some problems. It was reporting a different current to the app than it was actually running. They replaced it and since it has worked just fine. The charge controller has a Bluetooth connection to an app that allows you to set which battery you're using, the high and low charge settings that you want for the battery. It has a temperature sensor so that it will stop charging the battery if the temperature is too low or too high. It has automatic settings for lead acid and AGM batteries, and then it has manual settings that you can apply for any type of lithium battery that you want to use. Now the charging limit is 40 amps. So naturally, if you're charging a 12-volt battery, you're not going to be able to put in as much wattage as you would if you were charging a 48-volt battery. This can do 12, 24, and 48 volts, but 40 amps at 12 volts is only 480 watts, whereas 40 amps at 48 volts is over 1900 watts. So the configuration of your system will determine how much power you can get with this charge controller. Now you can put lots of extra panels on it so that even in a shady day, you can get the total power that you want to get. It just won't be able to utilize it all when the sun is up. So for example, right now I'm charging this ampere time lithium battery. The input voltage from the array, which is partly shady out, is 84 volts, and the current that it's putting into the battery is 26 amps. The battery voltage is at 14 volts, so we're putting about 370 watts into the battery right now. It'll track the peak voltage, the lowest voltage, and the total charge amount that's gone into the battery. And of course, as you saw, when the solar charge controller is maxed out at 40 amps, it dramatically reduces the load on your battery while you're running loads. So you can have the solar charge controller directly running your inverter, but you have to have a battery connected because that balances the load. The charge controller will deliver extra energy to the battery if it's delivering more than is required from the inverter, and if the inverter is calling for less, the extra power will go into the battery. Overall, this charger is a really great value. It's a really low cost point, and it has a very high voltage input, which is very helpful for managing optimal power consumption. It allows you to string a lot more panels together. This can take 150 volts in. Right now I have a 3S2P setup, so 3 panels in series, and those 2 sets connected in parallel, which gives me about 90 volts, which is a pretty optimal point for this system. Don't forget, when disconnecting your charge controller, always disconnect the PV first and then the battery. The reverse order of when you start it up. Always connect the battery first and then the PV. So to disconnect this unit, we'll disconnect the PV, easy to do with the breaker, and then I can disconnect the power from the battery. Now the unit is off and disconnected from the system. Now with the system no longer under load, I can disconnect the PV if I want to. And now we're completely disconnected and we can relocate the system. All right, let's see if this inverter can run a microwave. That's something that my Bluetti cannot do. This is a 950 watt microwave. I'll put a cup of liquid in there. We are pulling 9 amps, pulling the battery down to 12.2 volts. It is running no problem. 9.2 amps. Let's see what we're drawing from the battery. 78 amps. Ooh, water's getting hot. I'm going to turn off the... Let's see how much current we're drawing. 98 amps. So this is a 100 watt BMS. 99, 100. We're pulling its absolute limit. Now if I turn on the solar, now it drops down to under 80 amps because the charge controller is providing 22 amps. So you can see how when the sun is out, you can power more than your battery is able to deliver. Let's see. Ooh, yeah, that's hot. Well, that puts it right at its limit, but it did it without any problem. I mean, the fans didn't even come on the inverter. Well, the inverter is rated for a lot more than that, so we're not really working it that hard. But the battery BMS would have been right at its limit. All right, the microwave worked, no problem. All right, the Instant Pot is another device that the Bluetti couldn't power. Let's see if my DIY system can do it. Let's cook some porridge. All right, and we are at 7.6 amps. No problem at all. I can hear a slight hum, but the fans aren't even coming on. And that's going to be well under the 100 amps for the battery. So yeah, the hardest thing so far is the microwave. Let me see what else I can find. All right, the Bluetti could not run the Keurig. Of course, this is only 800 watts and the Keurig is 1740 watts. My inverter is only 1500 watts and the BMS is only 100 amps. So this would pull more than the inverter is supposed to handle and way more than the battery is supposed to deliver. So kind of curious to see what will happen. Ooh, 10 amps, 11 amps, 141 amps. Look at that. 141 amps it pulled to start. And it's working. 10.8 amps. Wow. 112 amps continuous. It's not even warm. Let's brew a cup of coffee. Look at that. 111 amps. No help from the solar. All done. Haha, it did it. Look at that. Full cup of coffee. Way over the rating of the inverter and the battery. And it pulled it off. Of course, it was only pulling almost 11 amps, so wasn't quite hitting its full power rating, but hey, that's pretty impressive. Let's see what the hot plate can do. All right, let's try the hot plate. The Bluetti couldn't run this one either. Let's see if our DIY system can do it. All right, here we go. Ooh, start low. 67 amps. Hey, it's working. All right, so it's pulsing on and off. You can hear it pulsing. We'll see if we can boil this liquid. When it pulses on, getting 8 or 9 amps. Okay, so we're pulling BMS limit there at 90 some amps. All right, well, let's bump it up to a higher level. But it does have a turbo mode. Let's see what happens. Oh yeah, now we're cranking. Woo! 130 amps. The BMS is not supposed to be able to do that. Water's about to boil though. Look at that. 12.1 amps. And a continuous 130 amps from the battery. Okay, so that's 1300 watts through the inverter. It's holding 110 volts, no problem. The inverter's fine. Boom, hot plate. Well, the pressure pot, the microwave, the Keurig, and the hot plate were all the large items that the Bluetti couldn't handle, and our DIY system had no issue with them. So that's pretty cool. Now I gotta find something that it can't do. What do I have? Hey, you guys wanted to see power tools. I'll try some power tools. This saw is rated for 15 amps, so that would pull 1600 watts. I'll set my meter to inrush to see how much it ends up pulling from the battery. Well, it cut it. It pulled 108 amps to start, but you could tell it was really pulling down when it tried to launch. All right, let's try that again. Well, it's not bad. I mean, it does cut through it, but you can tell the motor's really bogging down to get wound up, so it's probably not really the ideal solution for it. But, I mean, it works. So I guess I'd call that the limit of our DIY setup here. We'll have to look for something bigger to power the power tools. Well, to see if the limiting factor was the inverter or the battery for getting that motor spun up, I'm going to pull over the AGM battery, which has essentially unlimited current compared to this situation, and we'll try it again. Well, it pulled about the same amount of current, and I still had that slow startup. So I guess the limitation was the inverter, not the battery, which is surprising because that lead acid can provide way more current. So seems like we're just pushing that inverter right to the edge of its limit, but still pretty impressive cutting through 4x4s. I started this project to try and do a simple demonstration for 12-volt setups, and I had a single 12-volt ampere time battery. I had two EnjoyBot batteries I was going to put in parallel to show higher capacity solutions, and a 1500 watt low-cost inverter just to do a simple setup. However, when I started running things, I ran into some problems. This 1500 watt inverter draws over 200 amps when you turn the on switch on, and that triggers the BMS on this EnjoyBot to protect itself, and it shuts down. So I couldn't use it with this inverter. Now, if I put two of these in parallel, that doubles its capacity and it's able to run. But I wanted to make sure that it wasn't just the battery. So I bought a 1000 watt Renogy inverter to use with it, and it draws only 150 amps when you flip the switch on. And so that one works just fine with all of the batteries. For some reason, the ampere times 100 amp BMS is a little less sensitive, and it will tolerate the very significant spike that this inverter puts out. So now I have to do a little testing with the Renogy 1000 watt inverter just so we can see a comparison between them and make sure that there's a complete understanding of what works together and what doesn't. Now, because the EnjoyBot didn't work with the other inverter that I had because of the high startup current, I went out and bought a Renogy 1000 watt inverter. This is the most popular inverter on Amazon. And I have connected it to the EnjoyBot and it works just fine. It'll work with any of the batteries that I have shown today. It also comes with a remote switch to turn it on and off, which is good because this actually draws a lot more power in standby mode than the Alpha does. So it's convenient that you can turn it off when you're not using it, so it's not draining your battery down. It also comes with a set of cables. Now, these aren't nearly as heavy duty as the ones that we made in this video, but if you're not drawing a lot of power, they'll suffice. So if you're trying to do just a budget version and not spend a lot of money, you could get the 1000-watt inverter. It's a little bit cheaper, and it comes with cables and a remote on-off switch. It also has covers for these. I've left them off for illustration. To connect this up, we'll use our pre-charge resistor to make sure we don't trip the BMS. I just hold it there for about 10 seconds. See, no spark now. Go ahead and connect it up. Now with the meter set to inrush, I can turn on the inverter. And that pulled 138 amps to start up. A little less than the Alpha, but still pretty high, within the range of the EnjoyBot, so it doesn't trip it, and it's ready to go. So let's do a little bit of testing to see how much this 1000-watt Renogy can supply. The hot plate on turbo was one of the most difficult things to run, and the 1500-watt inverter was able to do it. So now let's see if the 1000-watt Renogy can also run it. I've put my clamp meter on here so I can track the current. Unfortunately, this one does not have a display for the AC current, AC voltage, and DC voltage like the Alpha does, but we can at least get an understanding of what it's drawing from the battery. So let's turn it on. All right, we're pulling 97 amps. So it's working, at least on regular level. Can turn it up to the highest regular setting. It just increases the pulse width. Maxes out at 97 amps. So let's see if it can do turbo mode. Whoa! The inverter shut down. We drew too much power. Either the inverter or the battery. Let me check and see which. Okay, on regular mode, we get up, almost 100 amps. The Renogy inverter is able to maintain that at 119 volts, so it's holding up the voltage really well. But as soon as we go into turbo mode, the inverter protects itself and shuts off. The microwave pulls 1500 watts, so let's see how well it does. 114, 115 volts. And 119 amps on the DC side. The cables are not even warm, but the inverter, of course, is way above its rated output right now. The fans are starting to come on, but it's able to handle it. So the Renogy inverter can put out way more than its rated capacity. So if you have anything that you're wanting to run that's 1000 watts or less, it should have no problem running it. This 1500 watts that the microwave was drawing was pushing it right to its edge, and the hot plate without turbo mode it can run, also pushing it, but it was able to do them. So really capable inverter. Maybe that's why it's #1 on Amazon. It will work with any of the batteries that we've been looking at. So that's another great choice. Now, if you're trying to start out with the absolute minimum cost, instead of buying a charge controller that you use solar panels to charge your battery with, if you want just an emergency setup, Ampere Time has this 20 amp charger, and it just plugs into the wall, and you can connect the little alligator clips to the 2 posts of your battery. And this charger is designed to charge these lithium iron phosphate batteries. Actually, it'll charge any brand battery. It does the proper ramp up and bulk charging and top off charging, and it does it very quickly. So for instance, if you knew there was a storm coming, you could take your battery, bring it from storage level all the way up to full charge just to prepare for the storm, and then use a 1000-watt inverter or even a 1500-watt inverter and just run it directly. And you don't need to deal with solar charge controllers, or anything like that. All you would need is a wall charger, a battery, and an inverter. And that is the lowest cost, simplest way to just get started with an emergency backup system. If you're going to be making your own DIY solar generator like this one that I put together for this video, there's a few things you're going to want to know before you pick the components that you want to put together. So let me break down some of the key differences between the components that I used in this video and why I would combine them the way I do. Then I'll go through some combinations and how much they would cost. For my testing, we know that a 1000-watt inverter is very capable, but there are a few household items that it can't power. And even though it can technically run the microwave, it's drawing 1400 watts, and that's way past this inverter's rating. For just a little bit more, you can get the Alpha 1500-watt inverter, and that can power pretty much any 120-volt load that I have in my house. If you want to be able to do multiple loads and not be straining your inverter, then I would go with the 2000-watt Renogy. Even though the 2000-watt Renogy comes with some 4-aught cables like this 1000-watt, I would go ahead and make my own 1-aught cables for anything over 1000 watts. You'll be drawing, in some cases, over 200 amps, and you won't have to worry about those cables getting hot. There are some characteristics that impact the compatibility of these components. First, the Alpha runs 110 volts AC instead of the 120 volts that you typically find in most US households. Now that's not a problem for most devices, but in some cases it'll drop down to 103 volts to conserve power under low loads, which is counterintuitive. Typically inverters will cut back their voltage when they see really high loads, but this one cuts back at low loads so that it can conserve power. So in the case of like running my refrigerator, for instance, it was able to run it longer than typical because it was running at a little bit lower voltage. The Renogy, on the other hand, holds pretty much 120 volts. At a very high load, I was able to pull it down to 118, but it is very close to 120 volts no matter what you're doing. So keep that in mind if the voltage is critical for the devices that you're powering. However, the key limiting characteristic for which components can go together is the inrush current that you get when you turn the switch on these devices. Now, you can use a resistor to manage the charging of the capacitors when you first connect the cables, but later when you turn the device on, there's another inrush of current. Now that inrush is not a problem if you're using AGM or lead acid type batteries. But if you're going to use a lithium iron phosphate battery, which is what I would recommend if you were making one of these, they have a BMS in them, or a battery management system. And those battery management systems have a load limit rating. The specs for the EnjoyBot and ampere time batteries are almost identical. However, their battery management systems do not operate the same. Typically, a BMS will handle much more than its rated value for a short period of time. Its job is to manage the charging and discharging of the lithium iron phosphate cells to prevent damaging or dangerous current flows. We can see from our testing that the EnjoyBot battery has a more sensitive setting for the max surge current. It will accept the 1000-watt Renogy, which draws 139 amps when you turn the switch on, but it shuts down when we connect the Alpha 1500-watt inverter, which draws 236 amps when you flip the switch on. So unless you're applying multiple batteries in parallel, or if you get the EnjoyBot with a higher rated BMS, it doesn't work with the Alpha inverter. The ampere time battery, on the other hand, even though it only has a 100 amp BMS, it can tolerate that higher current spike. I didn't purchase the 2000-watt Renogy, so I don't know what the inrush current for that inverter is, but I would recommend using a battery with a 200 amp BMS if you're going to use a 2000-watt inverter anyway. Because of that extra power, you would be drawing way more than the 100 amp BMS is rated for. A 2000-watt inverter, if you're running it at 2000 watts, is going to draw 170 amps from a 12-volt battery. Now, if you had two of these batteries in parallel, that's fine. You could pull that with no problem. But if you're going to have just one battery, I'd get the 200 amp BMS. The 1000-watt inverter draws only 83 amps at 1000 watts, and this 1500-watt inverter, when you're pushing it, would draw 125 amps. Now, if you just want to have the 1500-watt inverter to give yourself a little bit of headroom in case you hit those spikes, then that's fine. You can go with these smaller components, and I think it's okay to pair them that way, unless you're going to be pushing it all the time. So now let's break down a few of these DIY packages by cost and performance and compare them to a couple all-in-one systems that are available on the market. All right, starting with the lowest cost solution, a 12-volt budget emergency backup. You only need three components: a battery, an inverter, and an AC charger. Eliminating solar charging significantly reduces the cost. This system will power a full-size fridge for about 8.5 hours, and most TVs, computer equipment, and small appliances, no problem for a whole day. It can power everything a Bluetti EB70S can do, and then some, since it has a little bit more power and twice the battery capacity. If you want to see that video, I'll link to it at the end. Coming in between $700 and $750 though, it's not super cheap. But all the components can be used for future expansion, and it gets you started with a simple backup solution or temporary off-grid power. For the 12-volt budget solar setup, if you're off-grid, then you don't need the AC charger, and you can just eliminate that from your cost altogether. And you can replace that component with a solar charge controller, like this BougeRV 40 amp MPPT charge controller. I like this unit because it's in the budget category, but it comes with premium features, such as Bluetooth operation and monitoring, 150 volt PV input and 40 amp output. It can charge 12, 24, and 48 volt systems consisting of almost any battery type. Also, the lithium setting is fully customizable. If you're using the 1000 watt Renogy, you can use almost any 12 volt battery. All the ones I've tested work just fine with it. And coming in at a little over $1,000, it's a little bit more expensive than the base version, but it's very expandable. You can add additional solar and additional battery storage and build the system as you go. Of course, you can always shorten these wires up a little bit. They're a little longer because I used exactly the wires from my initial setup on the wooden board. Now, does it make sense to DIY this solar generator or buy this EB70S solar generator? This system is very comparable to the Bluetti EB70S that I tested. And when you compare the specs, you can see why the Bluetti is such an attractive package. It's more than $400 cheaper for a very similar capability. The DIY system does have twice the storage and better solar input capability, and it's expandable. But that's a lot of money to spend if you don't need those things. Of course, you can save $100 off the price I'm showing there if you don't get the AC charger. But the Bluetti does come with the AC charger, so to make them comparable, I added that in. If you don't need all the flexibility, yeah, it's a pretty easy choice. I'd go with the EB70S. However, for about $200 more, you can build this medium-duty setup that's a lot more capable. The boost to 1500 watts on the inverter makes a significant difference in what can be powered. As you saw in this video, the 1500 watt inverter can power every 120 volt appliance I own, and even makes a valiant effort to run the 15 amp miter saw. It's very expandable, and with just a single 200 watt solar panel, it can be completely recharged on a sunny day. And you can make a very compact portable version like this one. Everything's all in one place. It's completely portable. You can carry it with the strap that's already on the battery. PV connections available. Just disconnect the PV, carry it to where you need to supply power, or leave it set up this way. The hinge sides allow it to easily come right off the battery. All you have to do is unbolt the posts and spread the wings, and it slides right off. Let's look at a heavy-duty version. If you just want to have something capable that can run a fridge from sun up to sundown, we just need to make a couple of tweaks, upgrading the battery to a battery with a 200 amp BMS and a 2.56 kilowatt hour capacity, and upgrading the inverter to a 2000 watt inverter. You can achieve some operating margin. You won't be pushing the components to their limits, and you'll be able to power almost any 120 volt load at your house or RV. 400 watts of solar input would fully recharge the battery on a sunny day. The heavy-duty system is where the gap starts to close on the DIY versus buy solution. Compared to the very comparable Bluetti AC200P, the DIY solution on this chart is about $30 cheaper. So it's not the price that would push you into the DIY solution, but the flexibility. If you want to be able to expand and modify your system, DIY is the way to go. The DIY setup really starts to shine when you start adding extra battery capacity. However, if you want simple, easy, and portable, just get the Bluetti AC200P. Either way, if you're looking to cut costs, consider used solar panels. All of my latest installs have utilized used or clearance solar panels from Santan Solar. It's a great way to cut costs, and I have lots of videos on the performance of those panels if you want to check them out. I'll link to my cost summary and where to get all the parts in the description below. Using those links helps me bring more of this content to you. If you want to see how to make this portable solar generator, click this link or find it in the description below. This solar generator was a lot of fun to build, and I think you'll enjoy building